based on quantitative semantic features.
Thank you for the introduction. Like I said, my name is David Perry, and today I'll be talking about a project I've been working on with my colleague Daoyong Kim and my two advisors, Rupsha Samantha and Jingyu Zheng from Purdue University. In today's world, it seems like everyone wants to become a programmer. This is especially reflected in the fact that the classroom sizes of traditional computer science courses are staggering and growing drastically. In addition to this, massive open online courses have made computer science education available, and classes can sometimes have students of in the hundreds of thousands. And while this growing interest in computer science education is very exciting, it does present a logistical problem. This logistical problem is that completing the same instructional tasks that you do in traditional classrooms becomes very difficult to do when you scale up to classrooms of this size. So for example, solution analysis, where you try to go in and manually inspect programs to try to understand what your students are getting wrong or what kind of common errors your students are performing. Additionally, the task of feedback generation, where you attempt to find corrections to students' programs that can then be applied to correct their program and hopefully teach them what they've done incorrectly. And finally, grading, particularly in terms of partial credit, when you have to manually review student submissions and try to give them partial credit or understand what their misunderstandings were or slight errors were. However, fortunately, there has been some research in this area to try to automate these tasks and scale it up to large sizes. Specifically in today's talk, I'll be mentioning Clara, Overcode, and DPE. They all attempt to do some of these tasks. And specifically next, I'll be talking about some of the drawbacks that come with these systems, and specifically some drawbacks that Clara and Overcode have. For both of these systems, they start by receiving an incredibly large number of programming assignments from their students. These programming assignments are then divided into two sets by running them against an instructor's provided test suite. For programs that pass all of these tests, I'm putting them in the green box as correct. And then programs that fail at least one of these tests is incorrect, and I've displayed them in the red box. From here, the next step for Clara and Overcode is to examine the correct programs and put them into clusters based on their implementation strategies. These clusters are then used to compare incorrect programs and try to search for repairs or ways to fix the incorrect programs that directly correspond to feedback that you can give to your students. Unfortunately, this overall system has a few problems. The first problem is that in order to do this correct program clustering, we have to perform a pairwise number of program comparisons. So when able to do our correct program clustering, we have to compare each correct program to every other correct program. This comparison is actually typically very expensive, as it either compares the ASTs of the programs or has to do some kind of tree edit distance comparison. So when you add the fact that you have to do a large number of comparisons, and each one of these comparisons is very expensive, the fact is that this correct program clustering strategy is very expensive. The next problem is that this correct program clustering is largely based on syntax. To display how this is problematic, consider these two small snippets of code I extracted from some student assignments. Both pieces of code basically do the same thing. They have a while statement that executes while x is less than 10, and in the body of this while, we have an if statement that checks as y is less than 5. Conceptually, the main idea of these two pieces of code is the same. We iterate while x is less than 10, and once we enter the if statement, we never enter the if, or after we enter the if statement one time, we never enter it again. So if you look on the program on the left, this piece of code does so simply by adding a break statement in the if. However, the program on the right does this by adding a Boolean variable that it sets to 0 inside the if loop and checks to make sure it's 1 when entering the if statement. So while hopefully we can all see that conceptually these programs are same, regardless of small differences like the number of iterations one may do. But what's important to note is that tools like Clara and Overcode actually we'll separate these programs and say they're completely different implementations because of these small syntactical differences. Therefore, because you use syntax to cluster, and because it's so fragile, you end up generating an incredibly large number of clusters from your clustering system. Finally, the last problem I'll talk about with their systems are that clustering is restricted to only correct programs. We kind of mentioned this earlier, but what has to happen is that for every incorrect program, you have to make a comparison, a similar kind of expensive AST or tree edit distance comparison to at least one program from every cluster of correct programs. Therefore, you end up with, because you only cluster correct programs, you end up with this problem that you have to do another pairwise comparison between the correct and incorrect programs. So in summary, these issues are the fact that that the clustering itself, the way they do it in these systems by comparing them using tree edit distance or AST edits, is very expensive in itself. The fact that we're using syntax makes it where you have a large number of clusters, and then because you only cluster correct programs, you have to compare it to these large number of clusters. And when you add this all together, what you end up with is a system that is unscalable. So now I'll talk about our approach that we've implemented in a tool called SemCluster. From a high level, one of our contributions for SemCluster is that it's based on an entirely different clustering approach. We're no longer going to compare programs directly. Instead, we're going to convert programs into some kind of vector or quantitative representation and then feed those directly into machine learning algorithms. In order to do this, we're going to have to design a program feature vector that captures the semantics of the program. And then finally, I'll show an evaluation that really justifies the effectiveness of our approach and shows how it helps improve the performance of these standard instructional tasks. So I'll begin by talking about the clustering approach that is implemented in SemCluster. So like I said, we are going to come up with an entirely new vector representation for programs that captures its semantics. But another important aspect of this vector representation is that it has to allow us to compare programs by simply performing a Euclidean distance comparison between the vectors that represent the programs. And if we can somehow figure out how a representation that allows us to do this, then we can directly feed them to machine learning algorithms and generate clusters that are more accurate and more efficient. So if you remember how I described Clarion overcode working, these program clusters are generated by comparing each individual program. However, we're able to cluster all programs, not just the correct ones, by converting them to their vector representation and then feeding them to a machine learning algorithm, which generates clusters. Now, in order to do this, I've said that we have to describe the vector that we're going to be using to represent these programs. So this, unfortunately, is not very obvious. So what we did was we started to think about how programmers think when they first start either trying to solve a problem or implement a specific task. So the first thing we hypothesized that programmers think about is they think about how to partition the input space of their problem into equivalence classes. And we believe this is reflected in the decisions that the programmer makes when they're designing the control flow structure of their program. However, programmers also have to think about the computations that occur along these paths that they have partitioned out in their programs. Therefore, we have to somehow capture the essence of the sequence of the operations they choose and the order of operations and the type of operators they use when designing their program. So the first I'll talk about is how to capture the first one I discussed, and we do this with control flow features. And the main goal of this is to encapsulate the programmer's control flow decisions and come up with some kind of summary of their control flow structure. So what we're going to try to do is quantitate the abstraction, or create a quantitative abstraction of the input space partition that they've created. And then our control flow feature that we're going to calculate is going to basically calculate the number of inputs that trigger this specific path that we're modeling. The way we technically calculate this is by running the program on a set of tests provided by the instructor, and we basically record the execution path that each one of these tests trigger. We then model this path as an SMT formula and hand it off to a model counter. And this model counter returns the number of solutions that satisfy this formula. And this directly this number that it returns, this count, directly corresponds to the number of inputs that trigger this path of the program's execution, which is our control flow feature for that particular test. So now I'll give a trivial example. Consider you have a small program with only one if statement that checks if some input variable x is less than 30. The instructor has placed bounds on this input variable to say that all values of x are between 0 and 99. And the first test we use is that set x to 25. So obviously 25 is less than 30. So when it's executed, this program takes the true branch of the program. So then we would model this particular path and model count it. Because all values between 0 and 29 will satisfy this, or will take this true branch. We have 30 inputs that trigger this path, which is our corresponding control flow feature. Similarly, if we have an input from the test suite where x is 75, which of course takes the else branch of this if statement, we now count the number of inputs that take this else branch, which are all inputs from 30 to 99. Therefore, our control flow feature for that particular test is 70. Now, this may seem like a trivial example, but SemCluster is actually capable of handling much more complex and real code from actual students. This is two search algorithms extracted from some students' programming assignments. Both Search A and Search B implement depth-first search. In the light pink or orange, you can see highlighted, these are the small differences. They're very similar to the two pieces of code I described earlier. Essentially, they only want to enter this if statement once. One uses a break, and one uses a Boolean variable check. Now, it's important to note that tools like Clara and Overcode will actually separate these two programs, even though they both implement depth-first search. However, SemCluster is able to recognize that these programs are similar, and the way this is done is by, well, we'll consider one of the inputs that this program could be ran on. So this GA is a very simple graph that could be explored by depth-first search. And this input will trigger a path in Search A and a Search B. However, if we look at an equivalent input to this graph B, we notice that it will take the exact same paths in the same programs. So basically what SemCluster is able to do is count these number of inputs that fall into this same input equivalence class and use this information to determine if programs are similar or not. Unfortunately, control flow features are often not enough to completely distinguish the differences amongst programs. Therefore, we design another feature called data flow features. The goal of these features are to basically encapsulate the decisions the programmer makes related to data flow. So basically, we want to, again, capture how variables are read, how variables are stored to, and how variables are used in operations like arithmetic, etc. The way we calculate this is by instrumenting programs and executing them on various tests, and then analyzing the memory values from the trace, and from there we can kind of come up with this representation for data flow. So now I'll walk through a small example that kind of explains it. So again, we have a simple toy program with two inputs, variables x and y, whose initial value is 1. So we begin execution, and the first thing that happens is that both x and y are set to the value of 3. Therefore, we have a change of the value of the variable x and y from the original value of 1 to the value of 3. So we create a data flow feature for that change, and then we record the number of times it happens in the execution. So for this case, we have 2 instances where a variable changes from 1 to 3. If we continue execution, x gets incremented. So now we have a change from 3 to 4. So we create its corresponding data flow feature and set it to 1. Finally, we take y's value and set it to double the value of x, which in this case is 8. Therefore, we now have a change from 3 to 8, which occurs once in the execution. Now to summarize how we use this to cluster, like I said, we start by coming up with these tests, and then we execute them, and we then use these execution traces to build both control flow features and the data flow features for each program. We actually concatenate these set of features into one large vector we call the program feature vector, and then we directly feed these into a k-means clustering algorithm. And this outputs some clusters, which then can be used to enhance the performance of some of these traditional educational tasks. Now that I've talked about the tool, I'll try to justify it by showing our large evaluation that we've done. I'd like to point out specifically that On the next following slides, you'll see a drastically summarized version of our evaluation. And if you'd like to see more results, I invite you to read our paper. So the first evaluation we did was we started by considering the number of clusters generated by each clustering strategy. If you notice, for both Claire and Overcode, the number of clusters are very large. In fact, an order of magnitude larger than the clusters generated for SemCluster. Now, additionally, you should notice that DPE has very similar results to SemCluster, but DPE actually employs a neural network approach, and we'll talk a little bit about some of the drawbacks that comes with this approach later. The next evaluation we did was to try to show that our sorting algorithm our clustering algorithm could correctly sort programs based on their known implementation. So basically a ground truth evaluation. We thought these results were really exciting because we were able to take 100 programs from GitHub for both sorting and for graph search. We manually verified these programs for their implementation, and then used our clustering algorithm to separate them. And it was very exciting as we got a perfect result, able to correctly sort, quick sort, bubble sort, merge sort, selection sort, and also separate the difference between depth first search and breadth first search. This is especially exciting when compared to we performed this evaluation using Claire and Overcode, and we received a number of clusters that was far greater than what we received when using SemCluster. However, just considering the ground truth and the size of these clusters is not enough, but we also have to show that our clusters can improve the performance of repair strategies, which are typically used to generate feedback for students. So in order to do this, we compared SemCluster and DPE on our program set, and you'll notice two columns. The first column is in-cluster. For the in-cluster column, this is the percentage of time we were able to take a correct program and repair all other incorrect programs in the same cluster it belonged to. This is desirable to be high, and as you can see, both SemCluster and DPE do very well here. We also do another evaluation with out-cluster, or in the out-cluster column, that shows when we take a correct program and try to repair incorrect programs from different clusters that the correct program doesn't belong to. Again, we believe this should be low, as if a program is able to correct another program, they probably belong to the same cluster. The next thing we'll talk about a little bit is about the runtime performance that happens when you use SemCluster and these various strategies when clustering. So if you notice, for both Claire and Overcode, the time in seconds is much, much higher than for DPE and SemCluster. This is actually a result because of, if you look in the other column, this average column, this is the average number of comparisons that had to be done to find the correct correction. So if you look at both Claire and Overcode, these averages are very high because, again, incorrect programs are not clustered with their correct corresponding program, and they just are basically a random search has to be done. But because DPE and SemCluster are able to cluster them all together, the average number of comparisons is typically very low. So now I'll talk a little bit about the first drawback that DPE has because of its neural network approach. And that's basically that DPE requires a very large training set in order to build these dynamic embeddings that it would use for clustering. Therefore, we believe that DPE is not as deployable because there are many instances where you may not have a large corpus of programs that are the exact implementation of the program you're trying to cluster. Therefore, I'd say that DPE and SemCluster both can cluster programs and put them in small cluster sizes. They both have a high accuracy when it comes to repair when these clusters are used, but SemCluster has no training requirement like DPE does. The next drawback of DPE I'd like to mention is that DPE is very reliant on the training set and the quality of its training set. To show this, we kind of evaluated, we took the full training set for DPE and used smaller percentages of that data set to train the program from 60 to 90%. And as you can see, the results are much worse when you have much less data to train on. And in fact, the synthetic column is the only one that actually competes with our approach with SemCluster. And this approach is also difficult to deploy as it requires generating a very large number of fake incorrect programs that typically have to be manually generated or are somehow difficult to create. So in summary, I've presented our tool SemCluster. I've talked about how it presents or how it employs a completely different kind of clustering strategy for programs. We've done this by designing a program feature vector that captures the semantics of programs. And finally, I've shown our large evaluation that I think really justifies the effectiveness of our approach. I'd like to thank everyone for listening to my talk and open the floor for any questions. Thank you.
Thank you, David.
Thanks. That was a really interesting presentation.
Thank you.
The example where you gave the equivalent programs where you use break or use a Boolean. I teach first year programming, and actually the kind of feedback I often want to give to my students is, did you know you could use break? So in a way, I would want to probably regard those as inequivalent. I guess my question is, how tunable is the notion of what you'd like to be similar or not similar with the approach?
So it'd be kind of difficult to target specific things, but the number of clusters is tunable based on basically how many clusters you want to end up putting things on. And so how we've done this is that we look at the error, we look at some kind of error measurement to see the decide upon the number of clusters that we should choose. Like if you tried to single out a particular thing, like all programs that use break.
I mean, similarly, like if I'd asked the students to implement depth first search, maybe.
Right.
I wouldn't be happy if they just all implemented depth first search somehow. I would probably want to give some stylistic feedback about more elegant solutions and that kind of thing. So I guess I'm wondering, could it be useful for...
Right. So one thing that you would maybe consider is, which we've not tried, but would be interesting, is cluster all the programs based on their implementation and then take those clusters and then cluster them again with a more, with a heavier, or, requiring more clusters that time.
Okay. Thanks.
Yeah, thanks.
Really cool talk. Thank you very much. So you explained that you compute these control flow feature vectors using model counting and essentially counting how many inputs take a particular path through the program, from what I understood. So how do you handle input spaces that are infinite? Like if your input is a list or a graph or something, I would imagine there's infinitely many. So now maybe infinitely many inputs will take the same path through the program.
Right, so there has to be some kind of bound on the inputs given to the program. So these bounds could either be manually specified by the instructor, like if you, in my CFF or my control flow feature example, I said that, the input variable X has to be between 0 and 99. But you could also do it, you could also just derive it from the test suite that the instructor gave you, like look at upper and lower bounds of that particular test suite. Thank you.
Let's thank David again.